All right, welcome to Chapter 4, Measures of Variability. And what we're going to be covering in this lecture today is to understand, describe the purpose of measuring variability. We'll talk about ranges, so we'll define what that means and how to compute the range. Then we'll cover understanding variance and standard deviation. And then to close out, we'll calculate the sum of squares, variance, and standard deviation of a population. And then we'll talk about calculating the sum of squares, variance, and standard deviation for a sample. So variance, and understanding variance and how to quantify it is key to applying statistical analysis to data. Variability can be defined several ways. It refers to a quantitative distance measure based on the differences between scores. So how variable are your scores? Right? Variability describes the distance of the spread of scores, or the distance of a score from the mean, the distance of an average score from the mean, that is. So variability is a way of quantifying, assigning a numerical value to how variable your scores are, right? Let's take a sample of, say, 20 scores. Thinking back to an example used in a previous lecture, people are asked how much they like spinach on a scale of 1 to 5. If 20 people all said, all gave an answer of 3, so we had 20 3s in our sample, that would mean we'd have 0 variability. All the scores are exactly the same. Conversely, we might have half of the people give a score of 3, a quarter of the people give a score of 1, and a quarter of the people give a score of 5. Right? So this would yield the same mean as in the first example. The mean would still be 3. But now we've got some variability there. So now not all the scores are not exactly the same. There's some distance from one score to the next. So variability, calculating variability allows us to describe the distance of the spread of the scores, or the distance of an average score from the mean. Again, the purpose of measuring variability is to describe a distribution, and then to measure how well an individual score represents the distribution. And this is a real key point here. I urge you to read through this section in your text more than once until you get a good sense of why this is important to understand, right? Why it's important to get a read on the distribution of our data and how much variability exists there. It's important for us to know how far scores are from each other. This is going to become crucial when we calculate statistical tests. Okay, up until now, we've tackled different aspects of a set of data. We've tackled how data is distributed in the form of frequency distribution tables like the one in front of you right here, although there are no values there. How's the data distributed? Is it symmetrical distribution, kind of a normal or standard distribution with most of the scores in the middle at the average or the mean, the central tendency? Is the distribution positively or negatively skewed? We talked a bit about the central tendency, mean, median, mode, different ways to describe the middle point or average of a set of data. And we talked a little bit about another important aspect of the data set, how many data points are there, where we used big N for a population and little n for a sample, with n being equivalent to the sum of the numbers in the frequency column, right? How many scores are there? What is the sum of all of the numbers in the frequency column in a distribution table? So this lecture is going to be focused on a different aspect of data sets, and that's the amount of variability that exists in the data. Okay, so we're looking at a distribution table here, and I haven't provided any individual scores, but what I've done is provided you with n, little n, so this is a sample. N would be the sum of all the numbers in the F column, the frequencies for each score, and I provided you with a mean of 8. So let's look at some possible values that would fit these criteria of n equals 12 and mean equals 8. Okay, so here's a frequency distribution table with scores that meet that criteria. So the scores are 12, 10, 8, 6, and 4. And then in the frequency column, there are 0 12s, there are 0 10s, there are 12 8s, there are 0 6s, and there are 0 4s. So this is a sample in which there's absolutely no variability. Like the example I provided just a few slides back, all of the scores are exactly the same. So we'd say the variability in this case is 0. There is no variance between or among the scores. They're all the same. Now let's fulfill the same criteria of n equals 12 and mean equals 8 and introduce a little bit of variability. Okay, so now we've still got an n equals 12. We've sum all the numbers in the frequency column. Still end up with 12 scores and still end up with a mean of 8. But now I've got 2 10s, 2 6s, and 8 8s. So now we're starting to get a little bit of variability there. Not all the scores are exactly the same. Okay, let's introduce yet a little more variability. Okay, so here's another sample of data in which we've got 1 12, 2 10s, 6 8s, 2 6s, and 1 4. We still satisfy the criteria of n equals 12, mean equals 8, but now we've got even more variability. We've got a nice symmetrical standard distribution in front of us in which the mean, median, and mode is going to be 8. With a nice symmetrical distribution there. And we've got some variability in our sample. Let's increase the variability even a bit more. Okay, now we've got what we'd call a bimodal distribution. Right? We've got 6 12s and we've got 6 4s. But we still fulfill the same criteria. So I've shown you now this is the fourth sample of data in which n equals 12 and the mean equals 8. What varies across these 4 samples is the variability. Right? I've shown you increasing amounts of variability across each of these data sets, where the mean hasn't changed and the number of scores hasn't changed, but the variability has. So if we were to plot these different samples, what we'd end up seeing are quite different distribution curves. Another way to think about variability is to ask how much are the scores spread out. For example, here are 2 different distributions in which there is significantly more variability in weight than there is in height. So the figure on the left is showing significantly less variability than the figure on the right. Similar to the samples I just showed you, as the variability increased across those 4 samples, variability increases when we look at weight versus height. So most heights are clustered near the mean. You can see the mean there is 70 inches for adult height. Most of the scores are clustered pretty close to 70. For weight, we could say the mean is 170, and the weights are a little bit more extreme. There's more spread there. So when we look at variability, we're talking about how much distance is there between scores, how much distance is there between each score and the mean. Right? Variability tells us how well one score or our sample of scores represents the population of interest. Understanding variability allows us to conduct inferential statistics, and this is generally the goal we're after anyway. We've got a sample of data and we want to understand, does this sample represent the population at large? And so we look at variability to help us ascertain whether it does or not. Okay, and there are 3 measures of variability we're going to discuss today. We'll talk about the range, we'll talk about the variance, and we'll talk about the standard deviation. Okay, the range, the first measure of variance that we're going to discuss, it's a pretty simple concept. So the range is the distance covered by the scores in a distribution. from the smallest value to the highest value. Okay, and for continuous data, real limits are used. We talked about real limits before. So for example, for 1 to 5, the real limits would be 0.5, right, to 5.5. And then in order to discern the range, we would take 5.5 and subtract 0.5 from that to give us a range of 5. Okay, so the range is based on the two most extreme scores, the highest score and the lowest score. It's essentially the highest score minus the lowest score. But again, for continuous data, we'll use real limits. So it's based on two scores. It's not based on all the data, and it's a very imprecise, unreliable measure of variability. Ranges are usually mentioned when describing a set of data, but they're not used when we do inferential statistics. So they're not something that we'll cover very much in the course. The most common and important measure of variability is the standard deviation. So the standard deviation is a measure of the standard or average distance of any score from the mean. And it describes whether the scores are clustered closely around the mean or they're widely scattered. So it's simply an average variance, right? What is the average distance of any score from the mean? And the calculation differs slightly for populations versus samples. The basic concept of this is the same, but there's some slight variability in the formula there, which we'll discuss. Another important term to know is variance. And variance is a necessary companion concept to standard deviation, but it's not the same concept. So first we'll define what a standard deviation is. Remember, the standard deviation is the average distance between the mean and any given score in a sample. Okay, so there are a number of steps involved in calculating a standard deviation. The first is to calculate the distance between the scores and the mean. So X in this case represents all scores, and U, the funny looking U, represents the population mean. All right, so before we dive into the formula, here's the three samples I presented earlier, where N is the same, the mean is the same, but the variance is different. Right? So step one in calculating a standard deviation, which is the average distance between any score and the mean, is to calculate the distance between scores and the mean. So let's look at the first one on the left. The mean here is 8. The only score in our sample is 8. There are 12 of those. So if we were to calculate the distance between the scores, 8, and the mean, 8, what will we end up with? End up with 0, right? So there's no variability here. Therefore, the value of our standard deviation would be 0. There's no variance. The average distance between every score and the mean is 0, right? So let's look at the one in the middle. So there are 8 8s. So then again, there's no difference between those 8 scores and the mean. However, there are 2 scores that aren't 8. There are 2 10s and there are 2 6s. Right? So you can think about how far is 10 from 8? It's 2 units. How far is 6 from 8? It's 2 units. Right? In other words, 10 minus 8 is 2. 6 minus 8 is negative 2, but it's the same distance. So we do have some variance here. Before we move forward in the formula, just note that we do have some variance. Now let's look at that last distribution. We've got 6 8s, so there's no variability for those 6 8s. But we do have 2 10s and 2 6s. And we just calculated that there is a unit distance of 2 for each of those. And we've also got a 12 and a 4. And these are pretty far from the mean. There's a distance of 8 units between the 4 units, between the 4 and the 8, and 4 units between the 8 and the 12, right? So we've got more variability here than we do in the middle distribution. So again, the first step in calculating standard deviation is to calculate the distance between a score and the mean. So for example, in this first distribution, we have all 8s. So the score is 8, the mean is 8, so 8 minus 8 equals 0. For the distribution on the right, we do have some variability. We've got a score of 4. So calculating the distance between the score and the mean, 4 minus the mean, 8, equals -4. Let's pick a score from the middle distribution. We've got a score of 10 there. So we want to calculate the distance between the score and the mean. Take the score 10 minus the mean 8, and that gives us 2. Note that some of these scores were derived after this first step are positive, others are negative, and we will have to deal with that going forward, but just keep that in mind. Okay, so step 1 in defining a standard deviation or determining a standard deviation is to take the distance between each score and the mean. We're going to do that for all scores, right? We're going to do that for all the scores in a distribution. And we're going to sum the differences. Sum the deviations. The deviations again being the score minus the mean. The score minus the mean. That's the deviation or the difference. We're going to sum all of those. We're going to find a sum of deviations to use as a basis for finding the average deviation. So here again are 3 distributions. We're going to calculate the distance between every score and the mean, and then sum those scores. What you might want to do at this point is pause this slide and then execute step 1, which is to calculate the distance between every score and the mean for each of these 3 distributions separately. Okay, then sum the scores that are left over, the deviations. Okay, so if you did that on the last slide, you derived all of the deviations, right? And there should have been 12 scores for each distribution. So you should have had 12 numbers for each distribution. Then you would have summed all those numbers. Those would have been the deviations. You should have encountered a problem. And that problem would be that the deviations summed to 0, right? And this is because the mean is the balance point. So in the second distribution there, you had 2 scores that were 2 units away from the mean above it. You had 2 scores that were 2 units below, right? So you would have had, for your total number of deviations, you would have had scores of +2, +2, -2, and -2, which would have added up to 0. So if the sum is always 0, the mean deviation will always be 0. Right? But we know that's not true because we know all the scores aren't exactly the same, so there must be some variability. There must be some deviation there. So we're going to need a new strategy in order to solve the standard deviation. And that new strategy will be to remove the negative deviations by squaring all of them. So we're going to square each deviation score, and then we're going to sum the squared deviations. So we're going to be using this term a lot in this course. This is known as the sum of squares, SS. This is the sum of the square deviations, usually abbreviated SS. We need to get rid of the positive and negative signs. Understanding this is crucial to succeeding in the rest of the course. We need to get rid of the negative deviation so we can derive an average variability. And if we don't square them, they sum up to 0. Again, understanding the sum of squares is really crucial to succeeding in this course, and crucial to understanding and grasping and retaining the concept of variance that's going to be presented subsequently in future chapters. So a couple questions to consider. Can sum of squares ever have a value less than 0? Okay, so while you're thinking about that, you might consider, why is that the case? Well, no, obviously it can't, right? Because if we square a negative number, we end up with a positive value. Squaring any number is going to result in a positive value. So sum of squares can never have a value less than 0. Sum of squares could have a value equal to 0, as in the first distribution of those three I just showed you, the one on the left, where all the scores were exactly the same, well, then we would have had 0 squared plus 0 squared plus 0 squared plus 0 squared 8 times or 12 times, and that would have added up to 0. But we can never have a sum of squares less than 0. Okay, 2 steps. So we calculate the distance between each score and the mean. This gives us a set of deviation scores. Then we square each deviation score and we sum them together. And this number, the number we've calculated after step 2, is known as the sum of squares, or SS. Okay, so after performing step 2, the revised step 2, that is, we've now at least got a value that corresponds to the variability in our 3 data sets. Right, our first set, where all the scores were the same, that number is still 0, so sum of squares would be 0. However, the second set, we've actually got a value. Sum of squares is equal to 16. So we've actually quantified the variability. We've gone from eyeballing it to actually putting a value on it. We've got a number that we can assign to it, but the value we've placed on it is perhaps a little opaque. What does it mean, sum of squares? It's not a good descriptive measure. It doesn't give us a good intuitive sense of what the average value of any score in the distribution is from the mean. Okay, in order to get closer to something that's reasonably descriptive, we have to perform another step, which is to average the squared deviation. So average the sum of squares. And this is known as the mean squared deviation, also known as variance. So our variability is now going to be measured in squared units. So population variance equals the mean average squared deviation of the scores from the population mean. Okay, and the formula for variance is the sum of squared deviations divided by the total number of scores. This is step 3. So just to recap, we've calculated the distance between each score and the mean. That was step 1, arriving at a deviation score equivalent to the number of scores for each distribution. So there should be 12 different distances. Then we square each deviation score and we sum them together. This gives us a sum of squares. That's step 2. And then we're going to average the squared distance by taking the sum of squares and dividing it by n, right? The number of scores. If you look along the top, you'll see the sum of squares for each of these tables. And if you've been working along, this is what you should have arrived at for the sum of squares. So this would be the result of taking all of the deviations, squaring them, and then summing them. Now we're going to take the sum of squares and divide it by big N. And big N in this case would be 12. Because what we're really interested in is the number of units away from each score. Each score is from the mean. If we do conduct step 3, what we'll end up doing is taking 0, dividing by 12. That'll give us 0. We'll take the sum of squares for the second distribution. That'll be 16. We'll divide that by 12 and we'll end up with 1.333 repeated. And for the last one, we'll take sum of squares of 48 and divide that by 12 and end up with variance of 4. Okay, so now we're representing our variability in terms of squared units. Okay, we still haven't arrived at a standard deviation yet. So the population variance, where we are now, gives us a measure of variance within a sample. It allows us to compare different distributions and compare the variance across these different distributions, but it's not a very great descriptive measure. Right? We're dealing with squared units. Units don't really make sense regarding our data. The book cite's a good example of why population variance is not an accurate descriptor. Right, so the square distance from New York City to Boston is over 26,000 miles, but it's actually 162 miles. So 162 squared is 26,000. So 26,000 doesn't represent the distance from New York City to Boston. In the same way that a variance score doesn't represent the average distance between any score in a distribution and its mean. It doesn't describe the actual distance very well. We need to account for the fact that we square the deviation scores. Okay, so this brings us to step 4. The goal being to compute a measure of the standard or average distance of the scores from the mean. So variance measures the average square distance from the mean, and this is not quite our goal. We have to adjust for having squared all these differences by taking the square root of the variance. Excuse me. So the standard deviation is the square root of the variance. So putting this all together, we've got step 1, we calculate the distance between each score and the mean, giving us deviation scores for distribution. We square each deviation score, we sum all those scores together, this gives us the sum of squares. Then we average the square distance to get the variance. So we take the sum of squares and divide it by n, the number of scores. And then we take the square root of the variance. Okay, so the sum of squares is described above each distribution here. The one on the left, the sum of squares was 0, variance was 0, therefore standard deviation is 0. In the middle one, the sum of squares was 16. We divide 16 by 12, we end up with 1.333. If we take the square root of 1.333, we end up with 1.15, so the standard deviation is 1.15. That would be the average distance between any given score and the mean for this distribution. And finally, the last one. We end up with a sum of squares of 48. We divide that by 12, the number of scores, and end up with 4, so a variance of 4. And then we take the square root of 4, resulting in a standard deviation of 2. So again, standard deviation of 2 means that the average distance between any score and the mean in this last distribution is 2. All right, just to recap, we find that, so in order to calculate the standard deviation, we find the deviations between each score and the mean. If we were to add them up and compute the average, that would take us to a very much a dead end because the value would always be 0. So let's go back up to the top left. We find the deviation, the distance between each score and the mean, and then we square each deviation. We find the average of the square deviations. This is the variance. And we take the square root of the variance, and this is the standard deviation, also known as the standard distance of any score from the mean. The standard deviation provides a measure of the average distance from the mean. It sometimes appears as SD in all caps. It might be written SD in small letters, or ST period, DEV period. Okay, so now that you know what a standard deviation is, we can start using standard deviation to help us understand our data in a meaningful fashion. So if we've got a population where the mean is 80 and the standard deviation is 20, right? The average distance between any given score and the mean is 20. Would a score of 70 be considered an extreme value in this sample? Why or why not? What if the standard deviation was 5? These are questions we'll consider when we work over the some examples in class, but just some food for thought. Okay, just an example of what I'll expect you to be able to do after having worked through this chapter and become more familiar with the formulas is to take a histogram, like the one we're looking at here, and to derive the standard deviation of this set of data. Right? And you might do this by creating a frequency distribution table first, or you may not have to do that. This is a population. You can see some of the information is contained here. The population mean is 6. There are 5 scores, score of 1, 5, 7, 8, and 9. So given this, what you should be able to do from this point is calculate the standard deviation. Okay, so we've walked through a description of how to calculate the population variance in a data set and then arrive at the standard deviation. Okay, there is another way to calculate the standard deviation, which is known as a computational formula. This is described in your book. So the one we've just worked through is known as the definitional formula. The other formula is known as the computational formula. You will not be responsible for learning this for any tests or quizzes. To be honest, by and large, you're going to be calculating these statistics in the future, mostly by computer. After you leave this class, you absolutely will never do these by hand, again, for the most part. So you can kind of skip over the computational formula. It's not something I'm going to ask you to learn or memorize. Okay, so by this point, you should be familiar with these two formulas, and you should understand what they mean, what they represent conceptually. Given a set of data, you should be able to, a population of data, you should be able to calculate variance and standard deviation. Right, so the formulas for variance is sum of squares divided by n, and the standard deviation is the square root of the sum of squares divided by n. Variance is the average of squared deviations. So in regards to notation, we identify population variance with a lowercase Greek letter, sigma squared, so that funny looking O with the hair laid to the side there is sigma, and variance would be sigma squared, whereas standard deviation would be just sigma. All right, so now we're going to talk about standard deviation and variance for a sample. Up until now, we've been discussing how to calculate standard deviations and variance for a population. But most of the time when we conduct studies, we don't have access to the population. The population, again, if you recall, is the focus of our interest, right? The set of individuals that we're interested in knowing something about, which might be U.S. citizens or U.S. college students or Manchester college students. And we don't have access to the entire population or the resources to query all of them. So we are going to be limited to a sample from the population. And the goal of inferential statistics is to draw general conclusions about a population based on the limited information we get from a sample, which is merely a subset of that population. And samples are quite different from populations. So samples have less variability. There are less individuals in a sample. There are, say, maybe 30 or 40 individuals in a sample when the population is Manchester college students in a typical psychology study that comes from the psychology department here. Right, so there's going to be less variability in a sample than there is in the population. So computing the variance and standard deviation in the same way as for a population will give us a biased estimate of the population values. And just to represent this graphically, the population of adult heights forms a normal distribution. If you select a sample from this population, you're most likely to obtain individuals who are near average in height. We're not going to, in our sample, we're not going to have the most extreme individuals or all of the most extreme individuals in our sample, but rather we're going to have a subset of individuals who are pretty close to the average. So that as a result, the scores in the sample will be less variable than the scores in the population. And because we're going to make inferences about a population from our sample, then we need to make an adjustment in terms of how we calculate the variability of our sample to better reflect the variability of the population. So sum of squares is computed as before. But the formula for variance has n minus 1 rather than n in the denominator. So we're going to use n minus 1 when we calculate variance. And if we're going straight to calculating the standard deviation of a sample, we'll have the sum of squares divided by n minus 1, and then we'll take the square root of that. Right? And the notation uses s instead of the Greek letter sigma. So variance of a sample is s squared, and then standard deviation of a sample is s. Okay, so here's the previous example we worked through, or a previous example was the middle distribution from the 3 we worked through before, where the sum of scores is 16. The variance was 1.33, and the standard deviation was 1.15. and we took the sum of squares, 16, and divided by big N, 12, to arrive at the variance of 1.33. So this is a definitional formula for the standard deviation of a population. So now let's take a look at the definitional formula for the standard deviation of a sample. Again, you can see for a sample, we're going to use n minus 1 in step 3. So when we calculate the variance, we're going to take the sum of squares divided by n minus 1. Okay, so rather than 16 divided by 12, it's going to be 16 divided by 11, because n is 12. 12 minus 1 is 11, so 16 divided by 11 equals 1.45. And we're going to take the square root of 1.45, the variance, to get the standard deviation of this sample. Right? So the only difference between calculating the standard deviation for a population versus a sample is that in a population, the denominator is n, and in a sample, the denominator is n minus 1. All right, and just to represent this graphically, here we're looking at two figures, a population distribution on the left and the population distribution. You should be able to identify at this point the mean and the standard deviation of the population. So the mean is the little u at the bottom of the figure, 80. The population standard deviation is sigma, that equals 8. And then if we look at the figure on the right, we're looking at just a handful of scores from a sample. And in the sample, we've got a mean of 16. And again, notice the nomenclature, the capital N referring to mean, and then the S referring to the standard deviation. So the average distance from any score to the mean in this sample is 2. And remember, when calculating the standard deviation for a population versus a sample, the key difference in the formula is that we use n minus 1 in the denominator for a sample, whereas we use n in the population. So to recap, a standard deviation describes scores in terms of distance from the mean, and we can describe an entire distribution with just two numbers, right? The mean and the standard deviation. Okay, so here we're looking at a histogram. We've got all the data in front of us, but we've also got these two key numbers that allow us to kind of understand the nature of this, in this case, a sample, n equals 20, but the two important statistics are the mean, which is 36, and the standard deviation, which is 4. It's going to be really important to understand these concepts going forward. This is the point at which, if you're struggling a little, spend some extra time, listen to the lecture again, do more reading, work through the exercises, make sure you're in class so you can ask me questions, and so you can work through examples in class. Because from this point forward, we're going to be applying these concepts regularly and then building upon them. There are some inferences we can make given the standard deviation about whether a score is extreme or not, right? Generally, 70% or so of scores in a normal distribution or a standard distribution are going to fall within one standard deviation of the mean. And almost all scores are going to fall within 2 standard deviations, right? So for any given set of data, any sample of data, we should expect, in this particular example, 70% of our scores to fall between 32 and 40, one standard distribution away from the mean. And we should expect 95% of our scores to fall within 2 standard deviations. So 2 standard deviations in this case would be 8, right? Standard deviation is 4. 2 of those would be 8. The mean, 36, minus 8 would be 28. And the mean 36 plus 8 would be 44. So 95% of our scores should be between 28 and 44. If we look at this sample of data, we'll note that there's a score at 28, which is right at the 2 standard deviation point below the mean. And there seems to be one score above 2 standard deviations away from the mean on the high end, at around 45. So we might say, well, that's an extreme score because it falls outside of where we would expect 95% of all scores to fall. in a standard distribution. So what constitutes a high or low score in any given set of data is dependent upon the variability. Right? If the standard deviation was significantly smaller, in this particular case, with a different sample of data, a score of 44 would be even more extreme if the standard deviation was 2, for example. This is what we're going to be working on going forward when we talk about z-scores. One last concept I want to cover regards transformations of scale. So you may have some reason to transform a set of data. Say you had a set of data representing weight, and you find out that the scale that was used to collect the weight data was too low by 5 pounds, so you add 5 pounds to every score. So this is going to change your mean. Excuse me. It might be intuitive to you that the mean would change by 5 pounds if every score changes by 5 pounds. It's also important to note, though, that the standard deviation remains unchanged. So if you add a constant to each score, the mean changes, but the standard deviation remains unchanged. Now, if you multiply each score by a constant, the mean is changed, and the standard deviation is changed. It's also multiplied by that constant. For example, if you were converting from minutes to seconds, say, in which you'd multiply everything by 60. In conclusion, the goal of inferential statistics is to detect meaningful and significant patterns in research results. And variability in our data influences how easy it is to see these patterns. So high variability, so lots of variability, is going to obscure patterns that would be visible in low variability samples. We sometimes refer to this as error variance. And so to close, we'll just present you with 3 figures to make this point. These graphs show the results from 2 experiments. So in the experiment A on the left, the variability is small, and it's easy to see a 5-point mean difference between the 2 treatments. So maybe this is an experiment in which a drug was tested on some symptom. So we've got 2 samples, sample 1 and sample 2. After the drug treatment, the score of sample 1, the mean was 35, and sample 2, the mean was 40. Right? So we can easily spot the 5-point mean difference between treatments. It's not obscured by significant variability. Now, if we look at the data from experiment B, we see, okay, we've got 2 samples again. Similarly, we've got means of 35 and 40, 35 in white, 40 in blue. But we've got massive amounts of variability, so the 5-point mean difference is obscured by the large variability. So going forward, what we're going to start to do is try to quantify this variability. And that's going to allow us to make statements about how likely it is that there's actually a statistical difference between, say, 2 samples. And again, make sure you're feeling comfortable with how to calculate variance, how to calculate standard deviations, and that you understand conceptually what these mean, right? And you have a sense of why variability is important. Okay, because from here on out, we're going to be basing all of our future statistical tests on what we've learned in this chapter. Okay, next time around, we're going to transform scores into what are called z-scores, also known as standardized scores, using the mean and standard deviation to do so.